All right, good morning, chemists. How are we? So today we are continuing in Unit 4, Kinetics and Thermodynamics, continuing with kinetics. So our previous lesson was on integrated rate laws and how we can use those to determine concentration changing through time and also the order of reactions. Today we're going to be looking at kind of the whole picture. How do we relate all of these factors of the likelihood of collisions and activation energy together to kind of speak on what this rate constant is, K. So, we've been kind of just assuming, K is a given, right? But how is K actually calculated? So that's what we're going to look at today. And the equation that we're going to be using is called the Arrhenius equation. So, as we know with kinetics and kinetic molecular theory, in order to have an effective reaction, you have to have two things. Two needs need to be met. You have to have enough energy of a collision, and the collision with which the reactants hit each other has to have proper orientation. So, we talked about factors that can increase the rate of collisions, right? In order to increase the rate, you basically can heat something up, increase the concentration, increase the surface area, decrease the container size if that's relevant, and also generally, physical state can affect the rate as well. So aqueous or liquid phases or gaseous phases are generally better than the solid phase. We'll talk about all of that as we proceed. All right, so we know that K varies with temperature. So the rate constant K is set for specific temperatures, and what we've been looking at thus far, are given temperatures with given Ks. So how does this look, right? So if we look at this is experimental data for the hydrolysis of an ester. The reaction itself doesn't matter a whole lot, but if you look at these reaction conditions here, basically you've got the ester and water, which are the reactants, which are being held constant. As you can see, they don't change through any of the experiment trials. The temperature is what's changing. As you can see, the temperature goes up 10 degrees each trial, and the rate changes. The K also changes. So what they've plotted here is they've plotted temperature versus K. In order to calculate K, if you think back to when we write rate laws, right? Rate equals K times concentration raised to some power. So the rate law like this. If you plug in the experimental data, you can calculate K. So they probably just, they plugged in the rate, they plugged in the concentration, they know the order of the reaction, then you can calculate K. So what they did here is they calculated K at different temperatures, and as you can see, K increases exponentially. So it's not linear, and K is dependent on temperature, as we can see here. All right, this is the Arrhenius equation. This is how K is calculated. All right, so, the formatting of that equation is a little weird. So the Arrhenius equation sets K, your equilibrium constant, is equal to this term A. A we're going to look at in a moment, but A is the collision frequency factor. It's basically a factor that gives the probability of an effective collision, all right? E, that's your exponential E, the opposite of the log, the ln function, I'm sorry, raised to the negative E subscript A over RT. So apologize for the formatting there. The equation should look like this, where EA is the activation energy of the reaction, R is your gas constant, which is given, the universal gas constant, and T is your temperature in Kelvin. So this is how you can calculate K for a given reaction. This is where K comes from. If you know K, then you can also go back and back calculate these other terms. You can go ahead and calculate EA and A, which we'll see in a moment. If you take the natural log of both sides of this equation, so you take ln K equals ln A, and then with a negative exponential, that becomes a subtraction, minus EA over RT, right? This is a y equals mx plus b format here. So what I've done is I've taken the ln's of both sides just like they have, and then you have, you know, your y equals mx plus b. All right. So the ln a term is your b term. Your negative EA over r is your slope, and 1 over t is going to be your x. So when you end up plotting this thing, and we're going to see a plot in a moment, you have 1 over t on the x-axis, and you have actually ln of k on the y. And this is going to give you a line with a negative slope, and that slope, m, is going to be equal to negative EA over r. Your y-intercept is going to be ln of a. All right, so just to kind of give you a preview of what we're looking at here, this is how the equation kind of lays out on a plot. And if you look at this equation here at the bottom, they've gone ahead and they have kind of substituted experimental data so that you can calculate it from 2 experimental trials. So ln k2 over k1 equals negative EA over r of 1 over t2 minus 1 over t1. That's basically just doing y2 minus y1 in both directions. So again, here's our Arrhenius plot, just as I said. When you plot this as a line, your y-intercept becomes ln of a, your slope becomes negative EA over r, and your you should see a line here. And again, this is to show the temperature dependence of K. You can clearly see that K is changing with temperature here. K is changing with temperature. But the beautiful part about this equation and this plot is that it gives you an opportunity to calculate these other terms that are so important for kinetics. You can calculate the activation energy. So there's your thermodynamics term. And you can actually calculate this A term, this collision frequency term, which is really mysterious because it's really hard to, obviously it's not like you can see molecules colliding, so this isn't an observable thing. So to be able to calculate it is really cool. Keat, we talked about this. You asked if we could calculate it, and this is how you can do it. All right. So just to kind of remind us, kinetic factors also influenced by thermodynamics. Activation energy is the minimum amount of energy required to make a reaction run. So in order for a reaction to proceed, you have to meet or exceed the activation energy, right? So if you recall, if you have a reaction diagram, a potential energy diagram like this, where you have potential energy on the y-axis and the reaction coordinate is on the x, the activation energy is the amount of energy from the reactant energy to the peak. So this is EA here, right? And what we're saying about activation energy is you have to at least have that amount of energy to react. All right? And what the Arrhenius equation is showing is that because as temperature increases, well, basically what it's saying is that as temperature increases, the rate constant is going to increase. And we know that. Just kind of thinking, you know, about collisions in general, if you increase the speed of things, which remember, temperature is a measure of kinetic energy, so it's a measure of the speed of particles. If you increase the speed of things, then you will increase the rate of the collisions. If you increase the rate of the collisions, then the likelihood that an effective collision is going to happen will also increase. All right? Cool. Now, here's a calculation problem. So on the AP exam, they're not going to have you, well, they could have you use this equation in a number of ways. They could have you determine any of the factors. They could have you be calculating activation energy. They could have you calculate that A term. They could have you calculate K. So it's kind of a mixed bag, if you will. But as long as you know the equation and know how to use it, you will be good to go. Alrighty, so let's read this one. Determining the energy of activation. The decomposition reaction of hydrogen iodide is following. Has rate constants of 9.51 times 10 to the negative 9th at 500 Kelvin and 1.1 times 10 to the negative 5th at 600 Kelvin. Find EA. All right, so because they're giving you 2 data points, we know that we're going to be using that that second equation with the 2 variables, the 2 sets of variables there. Also, something to note: this equation is provided on the AP reference table. You don't need to memorize this. All right, so let's look at this. So if we copy this equation here, ln K2 over K1 equals negative EA over R, 1 over T2 minus 1 over T1. Okay, so here we are. And we're just going to go ahead and take those variables. So I'm going to say K1 is going to be 9.51 times 10 to the negative 9th. And T1 is 500K. All right. K2 is going to be that second K, so 1.1 times 10 to the negative 5th. T2 is going to be 600 Kelvin. Something that's really important, temperature always has to be in Kelvin here. So all you're going to do is really just plug into the equation and solve. Alrighty. So when you plug all of those terms into the equation, you end up getting this here, where again you've got your ln equals K1 over K2 equals to negative EA over R, 1 over T2 minus 1 over T1. Now again, you want to isolate EA. So you're going to have to move the R term and this temperature whole parenthesis thing to the other side. So you're going to multiply by R on both sides, cancel R on the right, and then you're going to multiply by the reciprocal of this temperature term. All right, so when you do that, you end up getting this equation here, okay, where EA is equal to negative R times the reciprocal of that temperature term. I just wrote a -1 exponent here because it's easiest. And then, of course, you keep the ln term as is. R is the gas constant. This is given on the reference table, 8.314 times joules per mole Kelvin. And when you go ahead and solve all of that out, here's the work here, you get 1.76 times 10 to the 5th joules per mole. Now again, this is an energy. This is activation energy, so joules is the unit, and standard is per mole. Very nice. Alrighty. This is a nice summary slide that kind of goes through all the different equations and ways that we've represented kinetic equations. Alright, so let's say, just to kind of recall everything that we've done. Alright, this is a very busy slide, but let's take it from the top. So the first thing that we did was, if you recall, remember if we were given an equation like this one up here, S2O8 plus 3I goes to 2SO4 plus I3, we could represent the rate of this reaction as changing concentrations over time. And recall, this was the first thing we did, and this is where, you know, it's showing taking the derivative as, you know, concentration changes over time, finding instantaneous rates. So this is where we stopped with the calculus part here. Recall that this is where you take the coefficients from the balanced equation and they become the denominators in this equation. So you've got, you know, the 3 comes from the 3 here. Okay. The second thing we did was we looked at changing concentration, comparing initial rate data to rate laws, right? So to determine the reaction order, looking at initial rates. And the key here is the word initial. So this was where, you know, you have to have the experimental data, you have to take each reactant one at a time, and you determine the reaction order with respect to each reactant. So this is where, you know, you end up writing a rate law that looks like kind of equation 2. Rate equals K, you know, and you determine the reaction orders, the exponents here, with experimental data. This is just an example. I don't know what the actual orders are. Okay. Now, the next thing that we looked at, right, so kind of step 3 here, was jumping down here to this integrated rate law and half-life. This is for, again, if you don't have initial rate data, you can integrate the rate law and then go ahead and go calculate the reaction order. So this is where you need to be familiar with these three equations here, right? So if the concentration equals concentration naught minus kT, that's your zero order, right? The ln equation, so this is zero order. The ln equation is your first order, and the 1 over A is your second order. So you're going to have to know those equations, right? And then finally, what we just learned today was the Arrhenius equation. So that's if you want to find K at various temperatures, or you want to calculate activation energy, you can go ahead and use the Arrhenius equation, which is this last one down here. So we learned a lot. Just to kind of summarize, this is the example. You do need to be familiar with how to use all of these equations. They all describe kinetics. Okay. Now we're going to kind of take a step back from the math, and we're going to look at what's happening at a molecular level here, and looking at collision theory. So remember that when we're looking at collisions, you have to think about the probability of one molecule hitting another. And this is actually represented in the rate law. This is why the concentration terms are multiplied and not added together. Because when you think about probability, kind of like in math, you have to think about all the possible combinations, right? So let's say, for example, you have, two A atoms and two B atoms, and you want them to collide to create an AB molecule. Atom A1 could collide with B1 or B2. And similarly, atom A2 could collide with B1 or B2. So when you're looking at the possible number of, effective collisions, it's not simply two, because it's not that you have two pairs of A's and B's. It's four possible collisions because you have different numbers of combinations. And you really see this amplified as you get higher and higher numbers of atoms. So if you just kind of zoom out here and look at the 3 by 3, as you can see, the collisions are going up kind of, in a multiplicative way. So each A has a probability or a possibility of colliding with any of the 3 B atoms. So 3 times 3 is 9. How does temperature come into play when it comes to the collisions, the likelihood of collisions? And this is where we're thinking about that A term. All right, so when we're thinking about this, we have to think about, at a molecular level, what's the likelihood that these things are going to collide? Okay, so let's look here. We're defining this F term basically just as the frequency of effective collisions. Okay, and if you look at this data, right, look at the dependence of these collisions on activation energy. So as you increase activation energy, even by just 25 kilojoules, you decrease the frequency of those effective collisions by a factor of 5. So by 100,000 times, you decrease the likelihood of those collisions, all right? Whereas temperature, when you increase the speed of those collisions, that varies, by a multiplication factor. So that's linear, not exponential, right? So let's look. If you increase temperature by 10 degrees, you approximately double the frequency of the collisions, right? It's not by a factor of 2, right? You multiply by 2. So very different dependence on, activation energy, that threshold energy requirement, and the speed at which particles move. Okay, and to understand this dependence, we have to think about, again, these collisions. Collisions happen when two particles literally hit each other. What is required? They have to be moving, right? And the speed at which they move will directly correlate to the frequency of those collisions. All right, so this looks very similar to the Boltzmann distribution that we've seen before. Remember that when you have a temperature, so let's say that, for example, in this room it's 70 degrees. Not every particle in this room is moving with that much kinetic energy. The average kinetic energy in the room is measured and reports a temperature of 70 degrees. However, there could be particles moving much faster or much slower than this. And we know that the particle speed distribution looks like this, a bell curve, right? And, you know, where the average speed would be the median, and it's on a distribution. We also know that as you increase temperature, that bell curve will shift and also flatten. So as you start increasing temperatures, your bell curve is actually going to increase and also flatten out. So something like this, right? This plot is very similar. So collision energy, basically activation energy, is given on the x-axis. The fraction of effective collisions, effectively that A term, is given on the y-axis. So as you can see, if you increase the activation energy, right? So let's say you were to increase the activation energy, move this threshold. Basically, you are excluding a lot more particles that would meet that threshold. So increasing activation energy definitely decreases the frequency of collisions. However, what they're showing here is what happens when you increase temperature. You allow more particles, you allow more collisions to meet or exceed that threshold, that activation energy threshold. So increasing the temperature will increase the frequency of collisions, increase the frequency of effective collisions as well. All right. When you look at a energy diagram, right? So this is basically a potential energy diagram. So it may look more familiar to you in this way. This is a very rugged plot. Okay, there you go. All right, now for a reversible reaction, the given reaction here is A plus B goes to C plus D, where your reactants are given on the left, your products are given on the right. The forward reaction is read from left to right. The reverse reaction is read from right to left. The activation energy is always the energy from the reactants to the activated state or the transition state. So as you can see from this plot, the forward reaction has a smaller activation energy than the reverse reaction. You can also see that the forward reaction is exothermic because the products have less energy than the reactants. And due to that, then the reverse reaction has to be endothermic because it follows a mirrored energy profile. All right, so just kind of going through that stuff. And again, if we're going to compare the frequency of collisions in either direction, the direction with the lower activation energy, that forward reaction, will have a higher frequency of effective collisions because more particles are moving with enough speed to make that reaction proceed. Whereas if you have a higher activation energy, you know, those particles will be moving at the same temperature, the same speed, so the likelihood of, you know, exceeding that energy threshold is much lower. All right, and again, this A term is not simply about the frequency of collisions, that F term, it also has to do with the orientation of collisions, right? So it's not simply, oh, as long as these particles hit with enough energy, the reaction proceeds. That's half of the problem. We know that the other half of the problem is, do these reactants have the proper orientation? So they have to hit with enough speed and the right geometry, basically. So the A term combines both of those things, frequency of collisions and the orientation of collisions. All right, and just to kind of review, you know, what is this molecular orientation thing? Particles, when they collide, they literally have to hit each other in a certain way. And most collisions are ineffective because you have to think about these molecules in 3D space. And you have a full 360 degrees of rotation available to you. And a molecule can hit you from any angle, basically. So the probability that you're going to have them hitting directly, you know, direct contact, proper orientation is low. And what we're saying is that if these particles collide ineffectively, so, in any other way, you won't have a reaction. Basically, these things are going to bounce right off each other and remain as reactants. Only when you have them hitting in the proper orientation can you have a reaction proceed. All right. Now, The reaction takes place at what we call the transition state, or the activated complex. The transition state is the peak of the energy profile. So when you're on that reaction energy plot, the transition state is the climax, the peak. And this is where you have bonds breaking and forming simultaneously at the same exact time. It's a very high energy state. It's extremely unstable, which is why it's so high energy in the profile. So when we draw transition states, they look different because you have bonds forming and breaking at the same time. So we're going to look at this example reaction here. We've got methyl bromide and hydroxide basically undergoing a substitution reaction. So the hydroxyl group is going to switch with the bromide. All right, and when we draw the transition state, this is what it would look like. So you've got the central carbon here, you've got its peripheral hydrogens, and the transition state is literally drawing the partial bond to bromine and to the hydroxyl group at the same time. So it's drawing the bond breaking between the bromine and carbon and the bond forming between the oxygen and carbon at the same time. So if you look at the reaction diagram here, I love this slide because it kind of gives you a molecular snapshot of what it looks like. You have reactants at the beginning, completely separate molecules, no, partial interactions there, okay? Then you have, as you start to, ascend the energy profile, if you will, you've got the hydroxyl starting to approach the carbon, right? And then at the peak of the transition state, that's where you basically have both of these bonds happening kind of simultaneously. So again, the bromine-carbon bond is breaking, the oxygen-carbon bond is forming. After the transition state, once you start going down that energy profile, your bromine is starting to leave the molecule. And finally, at the end, when you're left with just the products, the bromine has left completely and the hydroxyl group is in its complete bond. Now again, all of this happens instantaneously, but there is a physical exchange of electrons and they are literally relocating, so things are changing in space. All right, and lastly, transition states are considered to be identical for the forward and reverse directions. So, if we were looking at this reaction here, this transition state with the partial bromine, partial hydroxyl bond would be the transition state for the reverse reaction as well. That's not to say that these reactions will happen at the same rate. In fact, almost always that is not the case. The reason for that is because you have to think, if you're going in different directions, while you may be reaching the same transition state, you're starting with different materials. So in one direction, that collision may be much more favorable than in the other direction. And that will affect the speed at which these reactions proceed. And that's the whole basis of kinetics. So we've pretty much summarized all of our rate equations. We've talked about how to write changing concentration over time, rate laws, integrated rate laws. We've introduced the Arrhenius equation today. And we've also talked about, how do we tie together the thermodynamic activation energy and this, kind of ambiguous collision term. Hopefully we finalized some of those today and really tied a knot in the link between thermodynamics and kinetics. If you have any questions, leave a comment or shoot me an email. Good luck. I'll see you tomorrow.